Back everybody. In this video we're going to finish our discussion on addressing modes, and we're going to cover the last three that I've saved here. The three I's: indirect register, indirect auto increment, and indexed mode of addressing. Before we get to those three specific ones, let's recall what an addressing mode is in general. It's the way that the source and destination locations are specified in the operand of the instruction, which is usually a move instruction. And the MSP430 supports 7 different address modes. This video covers those three I's: indirect register, indirect auto increment, and indexed mode. These three are all related, so it makes sense to put them all in this wonderful video. The other 4 are covered in other videos, as we talked about. And again, I want to remind you that the amount of time the CPU takes to execute an instruction depends on these addressing modes, which is partially why we're covering them. And here's a snippet from the MSP430 Family Users Guide, so you can see that for yourself. Now, let's get to the specific indirect register mode. So this is the 5th one that we're covering in this sequence of videos. And in this one, and this is actually one of my favorite ones, in this one, the CPU register is storing a value that's going to be interpreted as an address. So it points to an address. The value in the register is interpreted as an address, and then that value, that address, is used to retrieve data. So if you know C pointers, this is the exact same concept, which is one of my favorite concepts, really, in programming. And we're going to talk about why we would do this, and if you already know why C pointers exist, then you're ahead of the game, so to speak. This mode of addressing is only valid for the source. To signify a pointer to an address, we're going to place the @ symbol in front of the register identifier, like R4, R5, and so forth. And in the MSP430 documentation, the indirect mode is denoted as @RN. And so here on this slide, you see a snippet from the Family Users Guide, so you can see the @RN in action. All right, so we previously said that the value in the register is interpreted as an address, and then that address is what's going to be used to retrieve data. So it's kind of a roundabout way of getting the data, and we ask ourselves, well, why would we want to do that? And the answer is this. If we treat an address as data, which is essentially what we're doing when we move an address into a register, then it can be manipulated, like incremented or decremented. This provides a way to access blocks of memory by incrementing the address pointer. There's a lot to unpack there, so if you want to pause, feel free, but I've got an example coming right before this little reminder. For the specific MSP430 FR6989, that's a lot there, the data memory begins at address 1C00. And I know this because I've looked at the guide, the data sheet online. Just real quick, just a reminder that the memory here is actually read-write memory, but colloquially known as RAM. Okay, so TI, Texas Instruments, has adopted that as RAM. So there it is. It starts at, again, 1C00. Here's our example, and we'll unpack all of this in just a second. But first, I want to point out to you that some of those operands there use the @ symbol. You'll see @R4, @R6. So these instructions are employing indirect register addressing, which is what we're talking about here. But you'll see that they also employ register mode addressing, like you'll just see in R4 and in R5, R6, R7. And they employ immediate mode addressing. You'll see the hashtags there as well, like in the first move instruction and the third move instruction. So again, you can mix and match, and part of my example here is to demonstrate the mixing and matching. All right, now let's look at the memory allocation at the bottom. So this is, I don't want to say executed, but we'll say executed anyway. But before the main routine is even executed. So when you upload this program into the MSP430, then immediately you have in data memory constant 1 is the address label for address 1C00, and then that is storing DEAD in hex, and then constant 2 is the address label for address 1C02, and that address is storing BEEF, beef. And why 1C00? Because nowhere have we specified 1C00. That's, again, because the data memory starts at address 1C00 for our specific MSP430 6989. All right, I also have the registers there that are going to be filled up in a second. All right, so that first move instruction, this is using immediate mode, which is putting 1C00, the constant 1C00, into R4. All right, so that's no big deal there. That's all there is to that instruction. Now the next instruction, there's a lot to unpack here. So what's happening here is that the contents of R4, which is 1C00, is going to be interpreted as an address. And that's because we have the @ sign in front of R4. So now that thing is pointing, notice the figure to the right, pointing to the address 1C00, and then what's stored in 1C00 is DEAD, dead, and then dead gets moved into R5 by that move instruction. If we had left off the @ sign in that instruction, that would move the contents of R4 into R5, so that would move 1C00 into R5. But with the @ symbol, that 1C00 gets interpreted as an address, and so then dead gets moved into R5. Okay, in the next move instruction, it's using immediate mode of addressing. So we've got the hashtag there, but then the word const too. And so const starts with a non-numerical character, right? And so it gets interpreted as an absolute address. This is the reason we have to put zeros in front of hexadecimal that starts with letters, so they don't get interpreted as an address. But this one we want as an address. It's an address label, so there's nothing wrong with that. Okay, so const 2 is a label for the address 1C02. So 1C02 now gets moved into R6. No big deal there. And then in the last move instruction, because of the @ symbol, 1C02 gets interpreted as an address, and that points to then that address location, which is storing beef, BEF in hex, and then that's what gets moved into R7. Again, if you left off the @ symbol in this instruction, then 1C02 would get moved into R7, not the contents at 1C02. All right, so I hope that makes sense. There's a lot going on there. Feel free to pause the video, but I think we're going to move on to the next mode, which is indirect auto-increment mode. This one is the same as what we just looked at, in that the register is storing something that is going to be interpreted as an address. But the difference is that the functionality is extended in that the address pointer is going to be automatically incremented. And that increment could be 1 or 2, depending on if we're operating on a byte or a word, if .b or .w is appended to the mnemonic. And this is only valid for the source. And to signify an indirect auto increment, we place the @ symbol like we did before, but we also place a plus sign after the register identifier. And in the MSP430 documentation, this mode, auto increment, indirect auto increment, is notated like this, @rn plus. And so you'll see here a snippet from the user's guide. There it is. So it auto increments. I guess maybe before before we look at this example, maybe we should talk about why it auto increments. And what we're going to use this auto increment for is, again, moving blocks of data. So if you are incrementing the address, then you can easily get blocks of data and access those and move those around, right? And so that's what this example is going to do. So at the bottom there, we've got memory allocation. Again, this is loaded before the main routine is even executed. So block 1, again, it's a label for address 1C00 because that's where memory begins, data memory begins in our MSP430. And we're using the directive .short, which is a 2-byte word, as opposed to .long, which would be 4 bytes. And so we're storing 1124, and then 3344, 5566, 7788, 99AA. And then because, again, block 1 starts at address 1C00, those, which are each 2-byte words, those will be stored in the addresses shown here at the top right. Okay, so the first move instruction, which is not indirect auto increment mode, what this does is it's going to take the address that block 1 is labeling, which is 1C00, and it's going to store that value in R4. So you see that there in the bottom right. No big deal there. Okay, now there's a lot to unpack in this instruction here. Now, R4, which is currently storing 1C00, that value is going to be interpreted as an address because of the @ sign before R4 in the operand. So it gets interpreted as an address, so it points to the value 1124 in data memory, and then that value 1124 gets moved into R5. Also, what happens here, though, is that 1C00, which was currently stored in R4, gets incremented. This is the new part. It gets incremented by 2 because we're operating on a word. So the assembler is smart in that sense, where it knows that we want to increment by 2 because we just got done operating on a word. So now R4, after this instruction is executed, is containing 1C02, which sets us up nicely to get the next piece in the block, right? That's the idea here. Okay, so when we move on to the next instruction, then again, R4 is currently storing 1C02, so that points to address 1C02, and then we get the data 3344, which we move to R6. Then, because this is auto increment mode, that R4 is incremented. It's incremented by 2 again because we're operating on a word. So now R4, after this instruction, is storing 1C04. Again, this now should be no surprise to you. After this instruction, or I guess during this instruction, 1C04 is stored in R4 at the beginning of the instruction. It points to data 5566, which gets moved into R7. Because it's auto increment mode, and we're operating on a word, R4 is incremented by 2 to 1C06 at the end of that instruction. That's all shown to the right. Now, the next one is different. The next instruction, that is different because we're operating on a byte. Okay, so now R4 is at the beginning of this instruction is storing 1C06, as we just said. So that points to 7788 in memory. However, we're just asking for a byte, and because this is an even address, we get the least significant byte there. And so we move 0088 into memory there, or not into memory, sorry, into register R8, as we show here to the right. So we move in 0088, and because we operated on a byte, then we only increment the contents of R4 by 1, making it 1C07. Again, We're operating on a byte here in this instruction. So currently R4 is storing 1C07, so we get the data 7788, but we only get the, 1C07 is the upper byte of address 1C06. So we're going to grab the 77 this time, and just because this is the example, just to illustrate this concept, and we're going to move that 77, then the upper byte, into R9. That gets stored as 0077 then. And again, because we operated on only a byte, then the R4 contents are incremented by only 1 to 1C08. Then on the last one here, 1C08 points to 99AA in data memory. We're asking for just a byte, so we're going to take, it's an even address, so we're going to take the least significant byte, AA, or the lower byte, AA, move that into R10, so R10 is storing 00AA, and then at the end of that instruction, we increment R4 by 1C09, and that's the final state of our program. And notice now we've moved a block of data from a data memory into the CPU. Nice, right? Forgot to say, I had to go all the way back to that slide just to say nice. All right, and then our final addressing mode here is indexed mode. And it's like the previous two. It holds the register holds something that's going to be interpreted as an address. So this one, though, is again extending functionality. It's going to allow a constant to be added to that address. We'll talk about why in a second. That constant can be is a 16-bit signed number, and it can be in any base. It's valid for the source and destination. That is, this addressing mode index is valid for the source and destination. To signify indexed mode, we're going to place the constant in front of the register identifier, which is in parentheses. And in the MSP 430 documentation, this mode is denoted as X parenthesis RN close parenthesis. All right. So like I said, this allows a constant to be added to the address. Why would we want to do that? That's useful when we want to access blocks of data in memory, where the offset between the blocks is known or can be calculated. So maybe we have two blocks of data, and we know the offset between those two blocks. That's when we would want to use indexed mode. So let's take a look at that. Okay, in this example, let's look at the bottom, memory allocation. So I'm going to define two blocks now. I'm going to define block 1, again, which is pointing, or is a label, not pointing, which is a label for address 1C00. And I'm going to store data AAAA at 1C00, but then BBBB in the next available slot, which is 1C02, CCCC in the next available, DDDD in the next available. And then I'm going to label block 2, which starts then, as you can see to the right, at 1C08. And I'm asking for 8 bytes of information. So 8 bytes would take us all the way through 1C08 in the address. And I'm also showing R4 here. Okay, so the first instruction there, this is no big deal. This is taking the block 1. Okay, block 1 is a label for address 1C00 and storing it in R4. So there we go. We're initializing R4. R4 now has something that we can interpret as an address. Okay, now the next instruction, you'll notice, first the syntax of the operand, right? But so what this is going to do, it's going to take R4 and it's going to interpret it as an address, the contents of R4 that is, and it's going to add 0 to it, so it's going to just leave it as 1C00. So that now points to AAAA in memory. And then the source, or excuse me, the destination of that line is also R4 with 1C00, but added a constant 8 to it. So now that points to 1C08, or the beginning of block 2 in data memory. So that's going to move AAAA to, or copy it to address 1C08 as shown there at right. Lots going on there. Feel free to pause the video, and maybe you can think about what the next instruction is going to do. Speaking of that next instruction, this one is going to take the contents of R4, which is 1C00, add 2 to it, making it 1C02, which is now interpreted as an address, and so that points to BBBB. And we're going to use the destination R4 plus 10, so that makes 1C0A. And so we move the contents, or copy the contents BBBB to that address, 1C0A. And similarly here, we're going to take 1C00, add 4 to it, making it 1C04. That gets interpreted as an address, so it points to CCCC. And then that's going to be copied to the contents of register R4 plus 12. So 1C00 plus 12 is 1C0C. And so we move CCCC into 1C0C. Lastly, in this last move instruction, we're going to take 1C00, add 6 to it. 1C06, that gets interpreted as an address and points to data DDDD. And then that gets copied or moved into whatever's in R4 plus 14, which is 1C0E, address 1C0E, as you can see here. So you can see if you know the offset, which is 8 in our 2 blocks, then we can move entire blocks of information, right? So again, notice we've moved one block to another. Also, I want to point out in this example, R4 never changed like it did in previous examples. R4 was stayed at 1C00. It was the instruction itself, or the mode of addressing, that actually added something to R4. Okay, so in this video, we looked at the final 3 address modes. And next time, then, we are going to start to look at data manipulation instructions. That's it. Thank you.